break and that you can still fit into your pants. It is important. Maybe you had the stretchy pants. Maybe you had, I don't know if anybody saw the stovetop stuffing pants. They have, Google it later, not right now, but they have like stuffing all along this, it looks like stuffing all along the side so that as you expand, so does it. It looks good. It looks good.
What?
Google it later. Stovetop stuffing pants. 3, 7, 9, 13, 16, 19, 21. Whoa! We are missing a whole crew.
Janet.
Destiny. Jeanette. Jackie. Michelle. Floor. And Axel. Why so many? 3, 7, 9, 13, 16, 19, 21. Alright, so we have got a whole lot of stuff to do. Please take out the unit guide. Find me over on page 45. Karina, we're going to start filming. Yep, that over there would be good. Okay, things that you need to know. Thing number 1, we have a test on Friday. In this ideal world where I controlled all the pieces before there was such a thing as Hurricane Harvey, we were going to take the test last week before Thanksgiving break. So that we would come home and come back and it was going to be brand new stuff and no tests. However, the test is this Friday. And the test covers 6 big topics. And I'm wondering if anybody remembers any of them. Henry, get me started. L'Hopital's rule is one of the things. Daisy, the mean value theorem is one of the things. Low D high minus high D low, 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 that's the quotient rule. That's not really one of the big things. We got L'Hopital's rule, we got mean value theorem. Diego. Implicit differentiation, implicitly defined curves. Paul.
Optimization.
Optimization.
Absolute maxima.
Absolute maxima, absolute minima, absolute extrema. Yes, extreme value theorem, all that. And the last thing is related rates. We're talking about related rates today. Chris, my God, why? It's going to be fine, Chris. Later today, I'm going to email you the solutions to a bunch of practice multiple choice questions that you want to work on sort of separate from homework that you're going to get yourself ready for excellence. It's going to be okay. It's all going to be okay. Let's see, there were also questions about, hey, this quiz that we took before the break that I didn't do so well. What can I do about that? I'm available today, Tuesday, and Thursday to work with anybody who wants to work on corrections to that quiz. Do I need to say that again? Monday, that's today. Tuesday during lunch, Thursday during lunch. At the end of the day on Thursday, if you have not met with me to work through the corrections, that grade is locked in and cannot be changed. However, if you meet with me, if we make the corrections, we do all those things, you're dissatisfied with this quiz grade, when you take the test on Friday, when the test grade is better, the test grade replaces the quiz grade. Adrian, you okay there? Excellent. 2 of my super smarties made it. Axel made it, and Destiny made it. And Destiny's not going to see how badly I spelled her first name. All right. I think that's it. BC students, that mid-unit assessment is on my desk, or I am not picking it up. And you guys have... That would have been nice when I got to my mailbox 35 minutes ago. Okay. So I'll go get that. You guys have stuff to work on, so you guys keep going. For AB students, tonight's homework is assignment number 63. Please make sure that you write this down. There are 5 problems there. You need to choose 3. All right, so with all of that out of the way, I'm going to take attendance. While I'm taking attendance, you're going to take a stroll down memory lane where we are looking at derivatives. It has been a while since you have taken the derivative of anything. I gave you Thanksgiving break off with no calculus responsibilities. This whole unit is on the derivative. It's applications of the derivative. Today we're going to do some new stuff with the derivative, but I need to see if you still remember the old stuff. So, on page 45, where it has this really nice evolution of man and computer, for some reason, laptops have gotten smaller, but men have gotten bigger. Don't make any guesses about the size of my laptop. It will end badly for you. Karina, you doing okay there? Mm-hmm. All right. So, take 3 minutes. Show me what you can do with these first 5 problems. Get help from a neighbor if you need it.
Bless you.
No, but remember the 8 goes in 4. No, yeah, but like,
Where's the no?
yeah, the original amount was the same thing. And then times 3. Yeah. So what if it is, you know, like would it be y
Okay, first one, f of x equals e to the 3x minus 2, so f prime, derivative of e to the power of stuff, is e to the power of stuff times the derivative. Hopefully everybody's totally 100% okay with that, no problem. Okay, Gonzalo, tell me about the second one here. Y equals 1 over t squared plus 1. How would you take the derivative there?
I did.
Okay, so tell me, what does that look like?
7 squared plus 1 times 0.
7 squared plus 1?
I'm sorry, t.
Okay, so low d high, yep,
minus parentheses 1 times 2t
1 times 2t,
all over t squared plus 1 squared.
t squared plus 1, the whole thing squared, and I hope everybody's okay with that.
Sure.
That's not going to be one of the answers on the multiple choice. I'm of course going to expect you to simplify this. Easy simplification, t squared plus 1 times 0, 0, and we're going to have negative 2t over t squared plus 1, the whole thing squared. And these are two that I would expect every single person in the room is feeling comfortable with. We've got this under control. Diego, how are you feeling about number 3? Okay, you see all the trig and you're like, no, I just came back from break. Karina, help them out. What are some things that we need to remember here?
well, ln, the derivative is 1 over stuff.
Okay, so if I just wanted to make a little note on the side, the derivative of natural log of stuff is 1 over stuff.
And then sine is
Uh-oh. Times the derivative of the stuff, right?
Yeah.
Yeah. So derivative of natural log of sine theta. Derivative of natural log of sine theta, you guys are all going to tell me is?
1
1 over
sine
1
theta
over the stuff. Not 1 over x, but 1 over sine theta. Times
Times cos.
derivative of sine, which is cosine. Like it, love it, that's the first term.
Yes, sir.
Plus, Garrison, this coming your way. Derivative sine natural log of theta. What's going on there?
The derivative of sine, cos,
Derivative of sine is cosine.
ln,
Cosine of ln of theta.
times 1 over x,
Times 1 over what?
theta.
1 of theta, yes. Okay, Jose, coming your way. Last part here, sine theta, ln theta. What derivative rule do you need here? Sine theta right next to ln theta.
It's been multiplied.
Okay, those are being multiplied, so what's the derivative rule that you need here? Oh, somebody help him out.
Product.
Product rule, excellent, Jose. Jose, tell me derivative of sine theta times natural log of theta. What's it going to be?
So cos of theta
Cosine theta
times ln of theta
times ln of theta.
Plus
Yep.
sine of theta
Sine of theta
times 1 over theta.
times 1 over theta. And that's good. I like it. I love it. It's a great answer, and I hope everybody's feeling okay.
Yes, sir.
Those cobwebs are getting cleared off. All three of these problems, though, these are called explicitly defined curves. Explicit, E-X-P-L-I-C-I-T. We talked about this right before we went on a very well-deserved break. Explicit means it's in like y equals form. I like to think of this as calculator-ready form. Not all problems, though, are going to come your way in explicitly defined form. Sometimes we have these implicitly defined curves. So let's take a look at some implicitly defined curves. Implicitly just means that the x's and the y's get mixed in together on the same side. The instructions here are going to be find dy dx. So we're going to go find the derivative. And since it's been a little while, let's go through this one together. X squared plus y squared equals pi squared. I want to find dy dx. Is everybody okay that this is implicitly defined?
Yeah.
Right, those x's and y's are mixing together on the same side. I want to find dy dx, so what's the derivative of x squared?
2x.
2x, good. Plus, what's the derivative of y squared?
2y times dy over dx.
This is 2y times dy dx. Because y depends on x. We're taking the derivative with respect to x. Equals the derivative of pi squared.
0.
Oh God, thank goodness. Nobody said 2 pi. You may have been tempted. 0. And now the last thing you need to do, what's dy dx?
So you subtract 2x.
Good, nice job, Daisy. You can subtract the 2x to the other side.
And then divide.
And then you're going to divide, so we get negative 2x over 2y. I like that, but even better, dy dx. Negative x over y, and I hope everybody's still feeling really good. We're comfortable. Jalissa, how are you feeling? All right, last one that we're going to do together, and then some new stuff coming your way. I want to find dy dx for e to the negative x minus e to the y minus 3xy equals 4x. Take a minute. Show me what you can do. Check with your neighbor. Yes. Kick you or shut up. This one's a little bit meaner. So Andy, you're right. E is a constant, but e to a power is not a constant. Like e to the x, e to the y. Okay, you are moving in the right direction. If you took the derivative of e to the negative x, and you got e to the negative x times negative 1. Minus the derivative of e to the y is e to the y, like it, don't love it.
Times dy dx.
It has to be times dy dx. With implicit differentiation, when you take the derivative of something that involves a y, because y depends on x, you multiply by the dy dx. It's a chain rule. Minus, now if you're going to make a mistake, it's this next one. And what we did, like before the break, we would say, all right, I know I need to take the derivative of 3xy, but I'm not really ready to take that derivative yet. So let me just put a little box around this and say I'm going to find the derivative. And the derivative of 4x is... Really? I thought it was 4. Okay. I need to take the derivative of 3xy. I hope everybody's okay with everything, and maybe this is the part where you slow down a little bit.
Yeah.
Gonzalo, do you have a question? Okay. So I've got negative e to the negative x minus e to the y dy dx minus, now I need the derivative of 3xy. Yvel, how are you feeling about this? How are you going to find the derivative of 3xy for me? You're going to do product rule. So tell me about your product rule there.
Well, I took out 3 and I just worried about the x.
Oh, you pulled the 3 out?
Yeah.
Okay. Can you keep that 3x in there? There's nothing wrong with what you did with pulling the 3 out, but I want to work with that 3x in there.
So then the derivative of 3. Wait, so you want 3x times y?
Right, 3x times y. What would that derivative be?
3
3.
times y
3 times y.
plus
plus
dx.
3x
No, dy over dx.
times dy over dx.
And
And all that is equal to 4. And I know Marilyn sees something. I think you're worried about a mistake that we're about to make. We need the parentheses because what we're saying is minus the derivative of that 3xy, so I need that negative to get distributed through. If you distribute that through, now we've got negative e to the negative x minus e to the y dy dx minus 3y minus 3x dy dx is equal to 4. That's good. That's great. We haven't figured out what dy dx is yet, but man, we are close. I don't know if anybody else can smell it, but I can. Marilyn, what do you got?
You add the e of negative x and the 3y to the other side.
Okay, why are you going to move the negative e to the negative x and the negative 3y to the other side?
Because they're not being multiplied by dy.
They don't have that dy dx term. We like to keep the terms that have dy dx on one side so that we can factor out the dy dx. So you'd have dy dx times, I'm going to do all the algebra at one time, negative e to the y, negative 3x, there's the 4, negative e to the negative x, we're going to add e to the negative x, check, negative 3y, we're going to add 3y. And the reason that you did this move is you want to be able to divide everything by what's in the parentheses. And finally, you're going to get dy dx equals 4 plus e to the negative x plus 3y over negative e to the y minus 3x. That's implicit differentiation. That is all the stuff that you know so far about derivatives. And now we get to do new stuff. All right. Is everybody mostly okay?
Yeah.
I really think you guys are going to be fine with related rates. We're going to get to do maybe 2 or 3 problems. I am going to check the homework that is due today. It's those 15 multiple choice questions that you did over Thanksgiving break. Don't worry, I haven't forgotten. But I want to capitalize on all of our derivative stuff before we do that. So I want to take you into this world of related rates. So I'm on page 46. Related rates problems are always going to be application problems. So they're always going to be word problems. They're almost always going to involve a little bit of geometry. And we're going to look at how things change over time. We're going to measure how things change over time. So let's look at this first problem. A 6-meter ladder is leaning against a wall. If the bottom of the ladder is pulled away from the wall at a constant rate of 0.5 meter per second, how fast is the top of the ladder sliding when it's 5 meters above the ground? This is a typical related rates question. It's going to be our first one. And because I have high expectations, I'm generally not going to give you a picture, but giving yourself a picture, creating a picture, would be a very good way to start this. So take a minute, read through this, see what you can do. We'll talk in a bit. Meter ladder, leaning against the wall, bottom of the ladder, away from the wall, concentrate.
Make like some sort of triangle.
Don't go all OCD on me. Don't worry about what kind of house is it. What's the wall made out of? Is it a metal ladder? Is it one of those folding ladders? Don't go all OCD on me. All right, if all goes well, oh, and it changed earlier. Oh, maybe it worked. There we go. Okay. If all goes well, hopefully you've got some sort of a diagram that looks like this.
Yeah.
You've got the wall, you've got the ladder. Jose, can you turn one of the lights off in the back? Okay. So you've got the wall, you've got the ladder. What's happening in this situation? Henry, what's happening?
The ladder is sliding down.
The ladder is sliding down. Why is the ladder sliding down? Is that what it says in the problem?
No.
No. It's
Pulled away.
away.
Pull away.
The ladder is getting pulled away. So like somebody's over here and they're pulling the ladder away from the wall. Now, Henry, you're right, the ladder's going to slide down the wall, and usually there's some calculus student at this point that gets confused and they're like, but wait, if I'm pulling the ladder away, shouldn't the ladder just pull away from the wall?
No.
No, that's not how things work in the real world. As you pull the ladder away from the bottom, what happens?
It goes down.
The ladder's going to go down. We're talking about how fast you pull the ladder away from the wall, and I'm asking about how fast the ladder slides down the wall. Everybody okay? All right, so just so that you can like see it and be like, ooh, I get this. Let me animate this. I want to slide the ladder. And part of the diagram does not work well. You'll see in a bit what's wrong.
Oh my god.
Anybody see anything wrong yet? You didn't see it wrong yet. Watch again.
You can't really hold it like
Here goes, here goes, here goes. Slide, 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 slide.
It doesn't slide away.
And for some reason in this diagram, the ladder bounces off the floor and goes back up the wall. That doesn't work. That's not actually what's happening.
I wish like
Okay. Everybody okay?
Yeah.
sir.
All right. So how fast is the ladder getting pulled away from the wall again?
1.5%.
A half of a meter per second. That's a rate. Derivatives are rates. Then I'm also asking the question about the ladder sliding down the wall. The ladder always gets pulled away at a half of a meter per second. What do we think about the rate that the ladder slides down the wall?
Same thing.
Same rate? You're pulling on the bottom at the same rate. It kind of maybe seems logical that you might slide down at the same rate. How many guys are going for that? You pull away at the same rate, it would slide down at the same rate. Okay, some people are willing to commit. Karina's like, nope, that's not going to be the way. Garrison, what are your thoughts?
Yeah, the rate that you pull the ladder is the same as it would go down.
Okay, so I want to show you a diagram here. This is going to be dy dt. The y dt is how the y value changes, how the height of the ladder changes. Watch what happens as I slide the ladder. What happens to dy dt?
The approach is
Fast. Reverse.
Okay, let it get past here and go back over to 0. dy dt,
Isn't that a vertical?
dy dt is getting more and more and more and more and more negative, meaning that as the ladder slides down the wall, what's happening? It's decreasing faster. It decreases at a faster rate. In fact, as you get close to 12, when the ladder should be right down at the bottom, it is like a super large negative number. It's moving down really, really fast, so fast that it's even kind of hard to see it. If you watch it, it's kind of slow, and then it starts to speed up, and maybe you're thinking about gravity and the way it just sort of pushes down. Love it. Let's look at the calculus. Jose, if you can turn the lights back on.
I like it.
So let's set this up. Hello, coming back. So, we've got the ladder. Now, the important thing with these related rates questions is we're going to have to figure out what things are always true and what things are sometimes true. What things are going to change, what things are going to stay the same. In this example, the ladder, is the length of the ladder changing or staying the same? It stays the same. It's always 6 feet. What about the distance from
6 meters.
6 meters? Thank you. Thank you for making me a better calculus teacher. How about the distance between the tip of the ladder and the building?
Changes.
That changes, right? Anything that's changing, we're going to give it a variable name. So I'm going to call it x. What else changes?
The Y. The height.
The height. I'm going to call it y. Paul, I heard you say something about like how fast things are changing. Great. But is everybody okay that the distance that the tip of the ladder is from the building changes? The very top of the ladder down to the bottom changes. But if you think like a geometry student, there's something here that is always going to be true. Diego, I heard you say it. What's the thing that's always true here? Pythagorean theorem. What does the Pythagorean theorem tell you?
A squared plus b squared equals c squared.
You're right. The Pythagorean theorem says a squared plus b squared equals c squared. It would be nice, however, if you could use my variables. For this particular problem, x squared plus y squared
equals c squared.
6.
How about 6 squared? Is everybody okay no matter what happens with the ladder, x squared plus y squared has to be equal to 6 squared?
Yeah.
Okay. What I want to do though is I want to talk about these changes, these rates of change. What we know is that the ladder is getting pulled away from the building at a rate. What was the rate? A half of a meter per second. That half of a meter per second is telling me how the x value is changing. Using my calculus knowledge, the way I'm going to write this is dx. It's how x changes. What am I comparing it to? Not dy. dt. I'm looking at how the x value changes with respect to time. dx dt is going to be a half of a meter per second. What I want to know is dy dt. dx dt is going to be a half a meter per second. I don't know what dy dt is going to be. Everybody mostly okay? Gonzalo, what's up? Okay. We're good with the equation. That equation is always going to be true. And so if this is always going to be true, this is what you can take a derivative of. Because this relationship's always going to be true. Well, what's the derivative of x squared plus y squared equals 6 if I'm looking at how things change over time? The derivative of x squared is 2x times dx dt. You may not have seen the dx dt coming, but x, how far the ladder is from the building, changes with time. It depends on time. So it's like a chain rule problem. So derivative of x squared is 2x dx dt plus, what about the height of the ladder?
2y times
It's going to be 2y times dy dt equals the derivative of 6 squared?
0.
0. That's the initial equation that we know is always true. What we did is we took the derivative with respect to time because we want to see how things change. Specifically in this problem, I want to know how fast is the top of the ladder sliding when it's 5 meters above the ground. So I want dy dt when y is equal to 5. Okay, thoughts? How are we going to get dy dt? Daisy, what are your thoughts?
I just had a question about back when you were taking the derivative.
Yeah?
I was wondering why even for the x squared you put the dx over dt.
Okay, good question. Y times dx dt when we take the derivative of x squared? Oh.
Because it still depends on time.
Because the x value, how far the ladder is from the wall, depends on time. Okay, we're measuring change with respect to time. Karina?
Do we plug in y to the original equation to find x?
Well, if what I want to do is find dy dt, I need to know what x is. I need to know what dx dt is, and I need to know what y is. We have some of those, right?
Yeah.
We know that y is equal to 5. So 2 times, sorry, that's supposed to be a 5, dy dt. Do we know what x is?
No. Just what I said.
We don't know what x is, but we know, we already established earlier, Diego told us, Pythagorean theorem, x squared plus y squared is equal to 6 squared. So what I need is the x value when y is equal to 5. So I can just plug in. So maybe I'd go off on the side here. X squared plus y squared equals 6 squared. X squared plus, what is that, 5 squared? I think. Square root of 11? What was that?
Is it 2x being multiplied times 1/2 meter per second?
Right, so we've got the 2. We did a little side work to figure out x is the square root of 11. dx dt, they told us, is this half. So plugging everything in, 2 times square root of 11 times a half, plus 2 times 5 times dy dt is going to be equal to 0. I want to get dy dt. So what, 2 times a half is going to be 1. What's that, square root of 11? Plus 10. dy dt is equal to 0. Is it negative? Negative square root of 11 over 10? Oh, hold on. I want to make sure everybody's okay with negative square root of 11 over 10. Before I take any questions, why is this negative? I want to get some hands on this. Why is dy dt negative? Andy, why is dy dt going to be negative? Love it. What's happening to the height? What's happening to this side as the ladder slides away? It decreases, right? That height decreases. So you have to have a negative here because y is decreasing. Okay, next question. What are the units? What do the units have to be? dy dt. What are we measuring the y value in? Meters. What are we measuring time in? Meters per second. God, I can't find a marker that's writing well today. Okay, everybody good? Last thing I want to do with this is I want to write this up. I want to get a good concluding sentence. And you guys should have it at the bottom. When you write your final answer, you need to tell me when is this true. At what point is dy dt equal to negative square root of 11 over 10 meters per second?
It goes 5 meters.
Okay, so let's be specific. When what?
When the top of the ladder is like
When the top of the ladder, is 5 meters above the ground, the ladder slides down the wall, and I know you cannot read that at all, at a rate of, don't blow it now, when the top of the ladder is 5 meters above the ground, the ladder slides down the wall at a rate of square root of 11 or negative square root of 11?
negative square root of.
No negative, Andy? Daisy wants the negative.
No.
What do you think, Jalissa? Use the negative or not the negative?
Wait.
Why not?
We already said that it slides down.
We've already said the ladder is sliding down. The height is decreasing. So at a rate of square root of 11 over 10 meters per second. Karina?
Shouldn't it be squared because it's like it goes fast from point one and like it changes velocity?
I understand what you're saying with the velocity. Yes, it is a velocity statement, but you're still measuring height in meters over time in seconds. Okay? The key with all these problems is going to be, number one, figure out what does this diagram look like? What's the geometry that connects everything? For this first one, it was pretty easy. We knew x squared plus y squared equals 6 squared. So from there, that's what you can take the derivative of. And then you're going to take all your rate stuff and plug it in. What I want you guys to do is get a running start on this one. If you flip to what is the homework assignment, since it's the first day back, I wanted to give you guys a little bit of time in class to get started on this. I'm looking over on page Here we go, 77. For the next couple of minutes, tonight's homework, you need to do 3 out of the 5 problems. I want to see what you guys can do with number 1 and number 2. While you're doing that, let me get some markers at work. Not that one. Barely that one. That one's
This is the hard
Morning. No, so I'm telling you that x is equal to 1 and y is equal to 2. So those would be x values and y values. So they're telling me that z equals x cubed times y squared, whatever. X and y are changing. At a certain instant, x equals 1 and y is equal to 2. X is decreasing the rate of 2 meters per second, and y is increasing. How fast is z changing? So you know that z is always going to be x cubed times y squared. How are you going to figure out how fast z changes? As soon as you get that one, like how fast is this changing? Walking around, most folks seem to be doing just fine with the derivative. dz dt, if I'm going to take the derivative of x cubed times y squared, product rule. So the derivative of x cubed is 3x squared. You're taking the derivative of x, but t is the variable. We're looking at how things change over time. So 3x squared dx dt times y squared. Right, because we're using product rule, take the derivative of the first, leave the second one alone. Plus, now what?
x cubed.
X cubed, leave that first one alone, times the derivative of y squared, which is 2y. 2y times dy dt. Getting the derivative, you're off to a good start. Yeah.
We have a problem where only x, like only one variable will have with respect to time. Like,
Talk to me more about that tomorrow. That's a good thought. But we're looking at, and you're told in the problem that both x and y are changing over time. All the friends are okay?
Yeah.
So I want to know dz dt when x equals 1 and y equals 2. Well, what else do we know? We know that x is decreasing at a rate of 2 units per second. So what is that?
dx.
X is decreasing at a rate of 2 units per second. That's dx dt. Dx dt is going to be, now I saw a lot of folks who said 2 units per second, and I like it but I don't love it. X is decreasing. So dx dt has to be negative. You're going to have to use that language of rates all the way through. Y is increasing at a rate of 3 units per second. So dy dt is going to be 3 units per second. We know x is 1, we know y is 2, we know dx dt, we know dy dt. I think we're cleared for takeoff. Right, everything should be good. dz dt is going to be 3 times 1 squared times dx dt, what is that, negative 2, times y squared, that's 2 squared, plus 1 cubed times 2 times 2 times dy dt. I know I'm totally in the way, sorry about that. It's 3. The new piece is taking the derivative. Everything I just did is I just plugged everything in. So what are we getting for dz dt? 3 times 1 squared times negative 2, and we're up to negative 6, times 2 squared is what, negative 24. 1 cubed times 2 times 2 times 3. It's going to be 12. So dz dt is negative 12. Henry.
When you did dz over dt equals 3 times, like, where did that 2 squared come from?
Where did the 2 squared come from? dz dt was 3x squared times dx dt times y squared from your product rule. Is everybody okay with getting to negative 12? Yeah. Okay, take a minute and give me the sentence. What does that mean? Don't read it to me, write it down. Yep, what's up, Andy? Why, when I did 3x squared, why did I do dx dt? Because we're taking the derivative with respect to time. We're looking at how things change over time. And so the derivative of x cubed is 3x squared times dx dt because x is changing with respect to time. I want to see that sentence. I want a perfect sentence. The perfect sentence, you're going to tell me when this is true, at what time is this true? I like to start with the when. So when x equals 1 and y equals 2, what's happening to z? Z is decreasing. Tell me more. At a rate of 12 units per second. I think for the most part, folks are okay. Really, it's just a matter of you're going to take the derivative with respect to time. You are going to have to translate some of their statements into rate statements. Your final answer, if it's a rate, you're always going to give me like a final sentence that explains that rate. So good news, I just get tricked into doing one of the homework problems. Tonight's homework, 2 more. 2 more out of the remaining 4. It does not matter to me which ones you pick. Some of these look really scary, and they're not. For all my AP Physics folks, you might want to go with question number 5. Or you may want to stay clear of that. That's your choice. All right, we've got just enough time for you guys to take out the homework you did over the break. There's 15 multiple choice questions. Let's take those out. If for some reason you did not do well, you have the opportunity to make corrections. If you didn't do it, you don't have that opportunity. But you'll see me during lunch today, so that uglier things don't have to happen. Not what I wanted to have happen. Oh, I know what's going on. All right, so if you could grab a marker, Paul, who am I passing these out to the back? There you go. Here we go. You just need to mark these as right or wrong and count them up. Number 1 ought to be C. Number 2, K. 3K. 4D. Number 5 is K. If we have time, I want to come back and talk about number 5. Number 6 is D. 7B. 8H. 9E. 10 is D. 11 is D. 12B. 13B. 14E. And 15D. 13 was B. So please count up how many you got correct out of the 15 that you did. Put that at the top of the paper. All right, I want to look at number 5. Okay, how many of you guys got number 5 right? Okay, 2 people, 3 people, 4 people, 5 people. Not as many as I would have hoped. Okay. Number 5 maybe doesn't start off looking too tricky. So this number 5, just make whatever changes you want, add whatever corrections you need to on there. E to the y equals x times y. Implicit or explicit?
Implicit.
Uh-oh, which one's which?
Implicit.
Explicit is like calculator ready, right? Like y equals f of x equals, type it into the calculator. So explicit or implicit?
Implicit.
Implicit. We've got everything mixed in together. The only thing I really care about with implicit differentiation is when I take the derivative of something that has a y, don't forget the dy dx. So the derivative of e to the y, you guys are all going to tell me is?
E to the y.
E to the y. Uh-oh. The derivative of e to the power of stuff is e to the power of stuff times that derivative. What's that derivative?
dy
dx equals derivative of xy.
Product rule.
Product rule. So we take the derivative of the first, which is 1, times y, plus leave the x alone, times dy dx. You want to solve for dy dx. I've got dy dx over here, I've got dy dx over here. We just need some algebra to move them together. So e to the y, dy dx, minus x, times dy dx is equal to, what is that, y?
Yeah.
Okay, factor out the dy dx. And then divide. And you get y divided by e to the y minus x. A perfectly acceptable answer. I'm curious, how many of you got here, but then could not find the final answer? Did anybody get here and not know where to go? Daisy, you made it here, but then you weren't really sure? Okay, I'll tell you, this answer is 100% correct. But those evil College Board folks are hiding it from you. Look at the answer choices. What are they doing? I really want to hear from somebody who didn't get this one right. What are they doing to hide this answer from you? Sheila, do you see it?
So in the beginning of the problem, they said e to the power of y equals xy.
In the beginning, they established this relationship that says e to the y. Every time you say e to the y, it's equal to xy. So what did they do, Sheila?
They plugged it in for that.
At the very end, when you did all the calculus right and you did all of your work, they said, oh, let me just make this a little bit harder for you. And they replaced the e to the y with xy. This answer is no better than this guy over here. They are the same, but on multiple choice, this is how they're choosing to hide it from you. Okay, make sure you leave the homework in the middle of the table. I will have these graded and passed back to you tomorrow. If for some reason I didn't just get it, I'll see you at lunch. Rebecca, you're going to stop by at lunch. Andy's stopping by at lunch. Chris, you're stopping by at lunch. Somebody else I said needs to stop by at lunch. Adrian, stopping by at lunch.